recording it. So, uh, is my screen visible?
Yes, ma'am, it is
Yeah,
visible.
yeah. So, since you're here, so let's start first discussing with the doubts which you had shared, and we are also recording it. So, okay. So, the first question which was raised is what is static condensation? So, uh, let's pick up this example, which was also done in the class. Let's say you have a frame. So, hence, let's assume that the beam is rigid. That is, a horizontal degree of freedom is good enough for describing its motion. And uh, so, wait? So, first is how do you define? Do you have an idea about kinematic degrees of freedom?
Yes, ma'am. The directions in which the object is allowed to displace
So,
is,
how many degrees of kinematic degrees of freedom does this frame have, assuming that the beam is rigid and the column is actually inextensible? So, columns can rotate, like
yeah,
these columns can rotate, and uh, you will have one horizontal degree of freedom. These three are the kinematic degrees of freedom for this frame. And when in dynamics, when we talk about degree of freedom, it is the independent display in the independent coordinates which can be used to describe the displaced configuration of the system. And here we are telling that all the mass is lumped at this floor level. So only required degree of freedom for dynamics is U1. So static condensation is the method by which you have, when you have in the kinematic degree of freedom, you have 3 degrees of freedom. From that, you are condensing the stiffness matrix, and you are getting only for this case only the lateral stiffness which is required for solving the problem. So I'll just give an example. So let's say this is the frame. This is height h. So these are the flexural rigidities of the frame. And first I want you to write, suppose we write something like this: k into u is equal to f. And suppose, what are the degrees of kinematic degrees of freedom? These are u1, u2, and u3. And in the direction of u1, let's say I have a force. um, I want to calculate the lateral stiffness of the frame. And let's say I have o- the only force acting on the frame is Fs. So this is Fs, and no other forces are there in the rotational degrees of freedom. So first I want to write down the stiffness matrix for this frame. So any idea how do we write such stiffness matrices? Have you come across the flexibility method?
yeah, ma'am, I have done stiffness matrix method. So,
So
uh,
let's just discuss one
yes,
column of this. So how do you write down the terms in that column? We apply a unit deformation in only that degree of freedom. For this, let's say it will be 1, and all the other degrees of freedom are restrained. That is, u1 is equal to 1, and u2 and u3 is equal to 0. That is only the uh, like if I draw the deformed shape, if this is the frame, we are just allowing u1 to be 1 and all the other rotational degrees of freedom are 0. So this beam will be straight. And I have to, what is stiffness? We know from here, like stiffness is F by U. So for a given value of unit deformation, we have to calculate the force. So for unit when u1 is 1, how much force is required to maintain this condition. So here you can simply use the fixed beam result. That is, when a fixed beam, you allow a deformation of delta, there are moments of 6 ei delta by L square, and moment is in this direction. So you will have a shear force of 12 EI delta by L cube, 12 EI delta by L cube. Now, suppose for the first entry, which is K11, that is force uh, developed in the direction of 1 because of restraint U1. So, how much will be this force K11? Let me- K11 will be this force. It will be uh, this term, but this is for only for one column. Since there are two columns, it will be 2 into 12 ei delta is 1 by what the length of the uh, column is h, so h cube, and eic. So is this term clear? That K11 will be this, because since there are two columns, that is why we have a factor of 2. And from this from the knowledge of fixed beam, I just used it here, and we get the first term to be 24 EIC by h cube. Now what will the second term be? That is K, let me call it K1 to K1 to K21 will be the same because of the symmetricity. But how much will be?
6 EI by L square.
So this length is L. Length of the beam is L. So it will be 6 EI by the height of the beam is h, so h square, and this will again be eic because this moment is coming into picture. If you can compare this beam to this column, you will get the results. So so in this way you can, and even this will be 6 eic by h square. So, and you can populate the entire matrix. So what you want is just the stiffness corresponding to, you want the lateral stiffness of the frame, that is the stiffness corresponding to this u1 degree of freedom. So what can you do? You can partition this matrix like this, and you can write that You should partition it like this. Why did I partition it? You'll just understand. I will also uh, let's not populate the matrix. Let's just write let's just write it like this. A B C D U1 U2 and U3 FS0 and 0. So you can write that A into U1 plus B into, can I write this equation? If I partition my stiffness matrix like this, simply C into U1 plus D times U2 times U3 is equal to 0. So can I write these two equations if I partition my stiffness matrix in this manner, where this term is A, this will be matrix C, this there will be this will be this B will be uh, so A will be 1 cross 1, this will be 2 cross 1, this will be 1 cross 2, and this will be 2 cross 2. So can I write these two equations, 1 and 2?
Yes, ma'am.
So from here, I can calculate U2 and U3 from equation 2. What will be U2 and U3? I will take this on the right hand side minus C U1 and 3 multiply with D inverse. So I can calculate U1 and U2 in terms of U1, and I can substitute this in this equation, which will be A times U1 plus B, and this will be minus D inverse C U1 is equal to Fs. Or I can write A minus B D inverse C times U1 is equal to Fs. So this term is nothing but the lateral stiffness of the frame. And what I did was static condensation. I removed these 2 degrees of freedom, which I did not require, and I got the stiffness corresponding to the degree of freedom U1, which I required. And this entire procedure is known as uh, uh, static condensation, and it is used to eliminate joint, majorly used to eliminate joint rotations. So is this is a brief introduction of like static condensation.
Yes, ma'am. So the matrix that we have now, that is K effective.
Yes, K effective, or the lateral stiffness of the frame, which appears in the natural frequency equation. A natural frequency is under root of K by M. This is that K.
Okay. So, ma'am, when I have a complex system, is this the only way by which I can calculate K effective?
Mm, what do you mean by a complex system? Here I removed only the degrees of freedom which I did not require. But let's
Right.
say you have a degree of freedom where there are, suppose here you had only one bay, right? Suppose you have a frame like this where you have 2 floors. So here you will have masses are lumped at this floor level and this floor level. So here you will have 2 degrees of freedom, and you can remove the other degrees of freedom, the joint rotations, like similar to what we did here. So by complex, do you mean a multi-degree of freedom system? Then no.
Yes, multiple springs, like also column could have axial deformations.
Then you need to keep those degrees of freedom. Then you might not use uh, this procedure.
Okay,
right? So this is like U2 and U3 are necessary in this process. If you remove them, it won't affect your solution. That is why I remove them.
got it.
Yeah. So one other question was why. So the natural frequency, another doubt was how is the natural frequency derived? That is, how is omega n under root of k by m? This, like as far as I have understood, like the suppose you have a spring mass system, the classical system which we are studying. So, and you apply a force P of t, the differential, and suppose x is the displacement variable. The differential equation is mx dot plus kx is equal to pt. And when you solve it, the kind of the like differential function, this equation, it is means, or you can say the solution of this equation is that of a simple harmonic motion. And in simple harmonic motion, terms like omega, which is the angular frequency, they make sense because in simple pendulum, the classical example which we study is you have a pendulum, you calculate its time period. Yeah, though there those terms make sense, and from there, I think so. This terminology has come into picture, that is natural frequency. So otherwise, I could not find any reason. If I get to know anything, I would let you know. So this is what is my interpretation. It is more of like a nomenclature thing. So this is my interpretation of natural frequency. So not a very clear answer, but I'll I'll try to explore this later on. So one more question is, how is the natural circular frequency derived using the static approach? So what you mean by the static approach is just you're uh, trying to relate. Uh, Suppose you have again a mass like this, but let's say now the mass is like uh, hanged. So what will be the static displacement? That is displacement of this mass due to gravity. So let's say delta static is equal to, it will be force by the stiffness k. Let's say the stiffness is k. Now what they are doing, since by definition we know omega n is under root of k by m, let's just substitute, use it here. Like with this, you know that k by m is g by delta static. So substitute it here. So omega n is under root of g by delta static. So is this the expression which you were referring to?
Yes, ma'am, this is the expression.
So did you want to like what was the doubt majorly? Like how is it derived or
How it is derived.
okay, so omega n I could write like this. Is this fine? Omega n. Then time period is 2 pi by omega n. So just substitute it here. So delta SD by G. So are the expressions clear now? So this is when you're studying a spring system like this, and delta SD is the deflection of the spring under its own weight. This is how delta SD is defined, and like with a certain definition, they are just calculating these terms.
Okay, so now only the doubt remaining is how omega n is under root k by m. That I will also see.
Yeah, this is something uh, like books refer it to as a definition, but uh, what I think so is just I was telling you this differential equation, the solution of a SHM fits into this equation, and they are relating it with SHM, and therefore the term omega n comes into picture. This is what I have understood. If there is any other interpretation, I'll let you know.
Okay,
I'll
yes, ma'am.
try. Yeah. So so I tried to do some reading work, but I could not figure out like why specifically this term is used.
Hmm.
So yeah, so the one of your next question was like how is the formula for amplitude in the case of undamped free vibration derived? So let's first write down the expression for undamped free vibration. So it is undamped for undamped free vibration. You have an equation like this, and we try to write an equation for the solution for this. I'll write down the solution first. So when you wrote down the solution, it was x of t is equal to x of 0 cos of omega n t plus x dot 0 by omega n sine omega n t. Is this solution clear? We had done this derivation.
Yes, ma'am, we had done.
Yeah.
I
So,
have a further doubt
mm-hmm,
regarding how I had a further doubt in that you'll see
mm-hmm.
how the differential equation has this standard solution of e raised to st.
Yeah,
But
so this is like you assume a solution, and you're putting it like you take that format and you're putting it in the differential equation, and it is satisfying it, like how like e to the power st we refer to it as a trial solution with where s is an unknown. This is a technique of solving differential equations. Like if
oh
there is some other form of differential equation, we choose a different solution, a
yes,
different trial solution. So this is a method of solving differential equation,
okay.
right?
Also, we have the solution in the standard form as a cos x plus I sin x.
Hmm.
Sorry, b sin x.
Yes. Yeah. So what we had derived, that x of t is a cos of omega n t plus b sine of omega n t. You're referring to this? First, we had derived it in form of e. I'll pull up my notes.
No, we said the general solution is a1 into e raised to s1t plus a2 into e raised to s2t.
Yeah, so we started with e to the power st, and we figured out that s1 and s2 is of this format, plus minus I omega n. So our
Yes,
general solution is a1 e to the power s1t plus a2 e to the power s2t. Then we used Euler equation, and we converted e to the power uh, uh, e to the power I omega n t and e to the power minus I m omega n t into cos and sine, because we just wanted to convert it into cos and sine.
right.
Uh, so this was the solution which we found out, that x of t is a cos of omega n t plus b sine of omega n t. And then we figured out a and b using the initial condition. And like
Also here we do have small deformation as an assumption, right?
here
Because
we
we are
did
using
not
Taylor
make.
series.
Mhm. Here we are
So
not using Taylor series.
The Euler's formula is derived from Taylor series itself. So,
Uh, but I don't think so. Here we are ignoring any terms because
okay.
this is also a series on the left hand side and this is also a series. So here we are not dropping any term.
Yes, that is also correct. We are not dropping. It is exactly the same Taylor approximation and this.
Yes, yes,
Right.
yes. So uh, in terms of A and B, you get the solution fine, and then you find out A and B in
Mhm.
terms of the initial condition, and this is the equation which you get. That x
Okay.
of t is x of 0 into cos of omega n t plus x dot 0 by omega n sin of omega n t, which I was right. Now, suppose I want to find out amplitude of this. So that was your
Yes.
doubt. So suppose you want to convert it into something which is, uh, let's say, sine of omega n t plus phi. So, or let's even make this simpler. Can I write this as, let me call this some constant a1 cos of omega n t plus b1 sine of omega n t, and let's say I'm dividing it by under root of a1 square plus b1 square by under root of a1 square plus b1 square. Okay, so I'll tell you what why I doing like this. So I want to convert it into some sine or cos. Suppose I want to write it, I want an amplitude, let's say x into sine of omega n t plus phi. I want to write it in this format. So what is sine a plus b? We know that a sine of a plus b is
Sine
sine
A,
a
B. So,
sine
sine
a
cos B.
cos b plus cos a sine b. I hope this formula is correct.
Yes. Yes.
Yeah. So if I relate these two equations, let's say A is omega n t and B is phi sine. So cos cos A is this. So x0 is sine B, x0 is sine B. Just compare this equation with this equation. And cos B is x dot 0 by omega n. Is this making sense?
Cos A.
No. A is omega n t. A is omega n t. So I have
Okay.
written it in a bad manner. So let's first write this down. x0 cos of omega n t plus x dot 0 by omega n sine omega n t. This is equal to, I want it to be equal to x of sine omega n t plus phi. This is what I wrote. Then I want x, and I'll open this, sine of omega n t plus cos phi plus cos of omega n t sine phi. Now can I compare left hand side and right hand side? So compare coefficient of cos omega n t from left hand side and right hand side. So on this side we have, so what I'm doing is I'm comparing cos omega n t. So x0, and here we have x into sine phi, and comparing terms with coefficient sine omega n t. So from this side will have this term x dot 0 by omega n, and here you will have x into uh, sine omega n t, then you will have this term cos phi. Now is it clear?
No, ma'am. There are
Uh,
two terms. So when we are comparing, so x naught cos omega nt will be
hmm.
compared with x sin omega nt cos phi.
No, cos omega n t will be compared with the cos omega n t on the left hand side will be compared with the cos omega n t on the right hand side. So on the
With the
left,
cos omega nt.
yeah, so on the left hand side, cos omega n t is multiplied with x0, and on the right hand side, cos omega n t is multiplied with sin x into x, sin phi into x. So this is what I've written.
Okay.
Similarly, in the left hand side, sine omega n t, the coefficient is x dot 0 by omega n. And on the right hand side, for sine omega n t, you have cos phi
Cos.
into x.
Yes. Got it.
So, so how will you calculate the amplitude x? I can square these two equations individually, and I can add, that is x, see, square of this omega n square is equal to x square sine square phi plus x square cos square phi. I can write this. Individually, I'm squaring equation 1 and 2 and I'm adding them. Now,
Okay.
sine square phi plus cos square phi is 1. So from here, I can write x is equal to under root of, so this is how I calculate x or the amplitude. Is this clear?
So ma'am, from where did we get x sin omega n plus phi?
This the equation 1.
No, when we
The
are comparing, so we are comparing it with x sin omega nt plus phi.
Yes. Where did I get this?
Yes.
This is something in which I want to express my solution. So, my solution is this big equation x0 cos and plus something into sine. Suppose I don't want to write such a big expression and I want to convert it into a form which is x into sine of omega nt plus phi. I want to write it in a condensed manner, in short. So, when I want to write it in a short manner, then what are the unknowns? The unknowns are x and phi, capital X and phi. So this is how I figure out capital X, which is the amplitude, and phi is the phase angle.
Okay, ma'am. I had probably done this.
Mm-hmm.
Like, is that an analogy for motion in circle when simply SHM equation generalize?
Yeah, you can relate it to that as well, because I am converting it into a sinusoidal function. Otherwise, how then only you can like plot, while plotting those terms on the plane. We use this analogy as well. We use the analogy of this phase difference and x there also. So it's
Okay.
just a way of expressing things, and carrying and calculating the amplitude and phase angle. Okay. So okay, if it's not clear, we can take this up at the end. So one more question is, how is the critical damping coefficient equal to, how is CCR equal to 2m omega n? This I think so is a definition, like how much I found in the book. This is something which you define to make our lives easier. Otherwise, I could not find any derivation of this thing. I'll still look into it. If I get any explanation, I'll let you know.
Okay, ma'am.
Okay, so uh, one more thing is, okay, then we discussed how do we calculate, like how is the gen. So for the other audience, one more question is, in a differential equation, how do we assume that this is the 12th solution? So this is a technique of solving differential equations, and seeing the form of the differential equation, we chose the solution and found out the uh, value of the constant involved in it. One more question is with regards to the viscously damped free vibration. So first, let's write down the solution for that, and then we'll discuss it. So in viscously damped free vibration, the equation which you are solving is this is what you are solving, and the solution which you get is xt is e to the power minus zeta omega n t, and let's say you have used the initial condition x0 that the at time t is equal to 0, x is equal to x0, and the velocity is equal to x dot 0, x0 cos of omega dt plus x dot 0 plus zeta omega n x0 by omega d sine of omega dt, where this omega d is equal to omega n under root of 1 minus zeta square. So, the envelope curve which ma'am was referring to is like just like we discussed above. You can bring these two terms outside, like how we were discussing. You can write this thing as e to the power minus zeta omega nt into rho into, let's say, some sine omega dt plus phi. I can write it like this, where rho will be x0 square plus x dot 0 plus zeta omega n x0 by omega d whole square under root. That's the same thing which we were doing earlier. So the only difference is like you have uh, 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 a exponential function multiplied at the front. So this is what ma'am was referring to be the envelope curve, because of which, like if you plot sine curve with a phase difference, let's say the phase difference is uh, 0, so it will be like this, but the amplitude will not decrease, it will remain the same, right? But because of this envelope kind of thing, the what is plot of e to the power minus x, it looks like this. So because
Mm.
of this, the amplitude, like when you multiply these two, as a result of this, uh, your response goes on dying out like this. So this is what ma'am was referring to as envelope curve. This is the terminology which she used, and which comes from the solution of this differential equation. And this is because of which, and your response is basically, it is enveloped between these two lines. This being e to the power minus zeta omega nt, your solution lies between in these two lines. That is why this terminology of envelope curve, I think so, she was using. So, could I at least partially answer your question?
Yes, ma'am. So what I understood is the terms that are defining dying down of the motion
Hmm.
is what is referred as envelope curve.
Yeah, because you can. think it in that manner also. Because of this, uh, the motion, basically the motion is contained between these two lines. It's enveloping because of that. Uh, the motion is dying because of damping, and damping appears in this part also, in the inner part also, because here you have omega d, because of which your period of the system is also changing. But envelope curve is basically because the motion is constrained between those two lines. So uh,
I still have confusion in the term row that you have written.
mhm, yes. So this is similar to what we were discussing here. Like here, we were just discussing. So in this case, how did we write the amplitude? It was x zero squared plus x dot zero by omega n whole square
Hmm.
under root. This is what we just wrote with reference to last day's notes. Here also, and this is when I am writing the form to be like some x times sine of omega n t plus phi. Here
Right.
also, in this square bracket term, I want to reduce it to something like x into sine of omega n t. Here instead of x, I'm writing rho.
Okay, so it is
Otherwise,
also similarly.
yeah, it's the same thing. Like you take the coefficient of cos and sine, and basically this is a trigonometric operation. Because I'm using sine of a plus b, those formula, and I'm basically like combining those things and writing a compact equation.
Okay.
Okay. Just have a look at those formula, and if you write them down, maybe you'll get a better uh, feel about this. It's you're just manipulating things here. What I feel. And one more question was with respect to how is the damping measured. So um, let's do the entire derivation. Maybe in the slides, I felt maybe one line is missing, which is leading to some confusion. So let's write down the derivation. So let's start from here. So for a viscously damped free vibration, we know that uh, your solution is of the form uh, x of t. I'm just repeating that equation, e to the power minus zeta omega n t, x of 0 cos of omega dt plus x dot 0 plus zeta omega n x 0 by omega d sine of omega dt. Right? Now, suppose this is uh, this is what you know. Okay. Now, what will be the response at this time, which is a period away from it? So, in place of t, I just want you to substitute t plus td, and then we'll understand what happens. E to the power minus zeta omega n t plus td, right? Then h0 remains the same, cos of omega t t plus td plus x dot 0 plus zeta omega square omega t. Okay, instead of writing this entire thing, I should have, okay, since I've written, just I'll complete it. Sine of omega t t plus td. Now, what is td? Td is the uh, period, natural period of the system. So after that period, in the sense, what do you mean by a period? The value of cos of omega t t and cos of omega t t plus td is the same. So if I take the ratio, I'll just be left with this term. Is this step fine? This is because TD is the period of the structure.
So we are taking TD to be multiple of 2 pi.
No, TD is period of the structure. That and here, yes, like what is TD? TD is 2 pi by omega t. So you can think it, t omega d into TD is 2 pi. It is uh, like why it's not multiple of 2 pi, it is 2 pi. And
Okay,
period, yes.
why I asked is because
Hmm,
only if cos omega dt is equal to cos omega dt plus TD.
hmm,
So this will only happen when they are multiples of 2 pi. Only then will they be always equal, cos and sine.
hmm. So here, let's say we are talking about only one cycle, that is 2 pi. For 2 pi, is
Okay.
this fine?
Yeah, fine.
For 2 pi, it's fine. So, okay, you are confused when there are number of cycles. Are you confused there?
I'm
Oh,
confused regarding the time period. If it is not 2 pi, then probably cos omega d into t is not equal to cos omega d t plus td.
here it is 2 pi. Do you agree with that in this
Yes,
situation? Because we
agreed.
are picking, uh, your situation is something like this. This is at time t, and this is at time t plus td. In this situation, is this fine?
Yes, ma'am, it is fine.
Yes. So, okay, so how can I like solve this? And I can write this to be e to the power, I can move this up, so it will be zeta omega n td. I can move this up. When I move this up, it will be subtracted. So is this this is fine, I guess.
Yes.
Yeah. So how can I write this? E to the power zeta. So let's keep zeta. TD can be written as uh, omega n. TD is 2 pi by omega d. And here I will also write omega d is omega n times 1 minus zeta square. So I will substitute this as well. So this is e to the power zeta omega n goes away, zeta 2 pi by under root of 1 minus zeta square. So what we get is x at I plus 1 is equal to e to the power zeta 2 pi, or 2 pi zeta by under root of 1 minus zeta square. Is this expression okay?
Yes.
This is fine. Okay.
Yes.
So let's take uh, logarithmic to the base e on both the side. So ln of xi by xi plus 1 is equal to 2 pi zeta by under root of 1 minus zeta square. And here the terminology delta has been introduced. Let's say this term is delta.
Okay.
And let's assume that damping is zeta is extremely small, damping is extremely small. So delta is 2 pi zeta. So this is the formula which was derived. So a twist to this, let's say you're not picking up just the adjacent cycle. Let's say you are picking up the first cycle and you're picking up j cycles away from that. That is, now you're taking the ratio of xi and or I should write, let's pick up the first cycle and then the jth cycle. Okay, so here the difference was Td. Now the difference will be J times Td.
Right.
Okay, so this I can write to be x1 by x2, x2 by x3, and this will go up to x, let's say j by xj plus 1. I can write it like this. This left hand side and right hand side is same. This term will go away, this will cross, and they are equal. Now, this
Mm.
this term, let me write it here. This I'm referring to be as delta. So xi by xi plus 1 is e to the power delta. So x1 by x2 is e to the power delta, x2 by x3 is e to the power delta, and how many e to the power delta I have? J times, because
J
there are
time.
j cycles. So if I take uh, ln on both the sides, so ln of xi by x1 by xj plus 1 is j times delta, or uh, let's say uh, delta is 1 by j times ln of x1 by xj plus 1. And from here we know that delta is 2 pi into zeta. So this is equal to 2 pi into zeta. And from here I get an expression for damping. That is zeta is equal to 1 by 2 pi j ln of x1 by xj plus 1. So this is the final expression which is used in problems. Like I think so. One problem was also discussed in this week's lecture. So is the doubt clear? Like I
Uh,
derived the entire expression. So what
yes, ma'am.
was the particular doubt?
Now, two doubts. Zeta is critical damping coefficient, right?
Zeta is just the damping coefficient. Zeta is just the here you
Okay.
CCR is critical damping. This
Okay.
is just damping coefficient.
Okay. Now clear. And the one doubt that is remaining is TD, regarding TD, that
Hmm.
the period is in multiples of 2 pi, or how are the terms getting cancelled?
Because here if I at this stage, if I open my bracket, it will be, suppose I open this square bracket, it will be x0 cos of omega dt plus omega d into td. And what is
Right.
omega d into td? 2 pi. And what is cos of omega d td plus 2 pi? I can write this as omega dt, right?
Yes. Got it. Yes.
Similarly, I can write this to be omega d into t. Like it will be 2 pi because of this fact. Here,
Yes, ma'am.
and here, whatever we discussed, it was in terms of the single cycle. And when you think about multiple cycles, uh, thinking it in this format is easier. Otherwise you'll get confused here, that whether
Hmm.
there are even number of cycles or odd number of cycles. So let's not think it in that manner, think it in this manner, and if the math makes sense if you think it in
Yes,
this
ma'am.
manner. Okay, so this is one more thing, and the last question. I could not like exactly understand this question like you had asked. So for the other audience also, I'll elaborate the question. This is with respect to the energy dissipation in I think so in a viscous damper. So here the question asked was, like the expression highlighted is, if ed is equal to integral of fd into dx, the force in, what is the force provided by a viscous dashpot? C into u. Now we know that u is the sorry, C into u dot, or I here what I feel you should have, like the nomenclature should be x dot, and distance, what is x dot? It is dx by dt. So dx can be written as x dot into dt, and this is how we get the expression, and you can integrate it over time. So, what was your first particular doubt first? And another thing which I cleared just now is maybe the nomenclature. There is a small problem in the nomenclature because we are writing x's also, u also, that is creating a confusion.
Yeah. Yes, ma'am. This was the doubt as how dx is substituted by u into dt.
So, this is what is actually being done. And when you integrate this, you will, and you have all, one more doubt was also asked, that if the force is half into p. So here, let's say, let's assume a simple case, that the this is
Huh.
x
Yes.
axis, this is f axis, f, sorry, f is k into x. So if you have to calculate the energy dissipation, it is actually the area under this triangle, let's say. At this point, if the force is capital F, displacement is capital X, it is half into F into X. But you can get this from integration as well. This half is a, how do you get it from integration? Your force is K into X and dx is this. You integrate it over 0 to x. So k x square by 2, and the limits are 0 to x, and you get k, this should be capital X, k x square by 2. So whether you think in terms of geometry or you get it from integration, your energy is the same. And this is how that half comes into picture because of integration. So is this clear?
Yes, ma'am.
Okay. So, uh, so okay, let's move on to this week's content. So, like, this
Yes,
was a
ma'am.
very okay.
I have one doubt.
Mm-hmm.
This is in relation to the Coulomb's damped-free vibration.
Mm-hmm.
So, ma'am, so the displacement amplitude diminishes with a coefficient of 4 times f by k, isn't it?
True, true, true. Yes.
So, ma'am, one assignment question was there
Mm-hmm.
that the initial amplitude was given 200 mm
Mm-hmm.
and 4f by k is coming 25.3 mm.
Okay.
So the
Initial
question
is
is
initial
200
is
mm, 200
initial
mm.
is 200. Fine. Huh. Okay.
And the question is ki how many cycle it takes
Mm-hmm.
to stop the
Mm-hmm.
motion.
Mm-hmm.
So in 7 cycle, if you calculate 25.3 into 7,
Mm-hmm.
it comes to 177 mm.
Mm-hmm.
And the remaining amplitude in that case will be 177.1 minus 200 mm
Mm-hmm.
is coming 22.9 mm.
Mm-hmm.
And we have been taught that for starting a cycle, the amplitude should be more than f by k. It is
True,
not 4f by k.
true.
So after 7 cycle, it will take one more cycle or it will stop.
It should take one more cycle.
Okay, so the
Like
answer is
with the math, like if like what with what the numbers which you just told me, because it has that remaining.
so the answer would be 8, na? 8 cycle it will take
Mm,
to diminish the entire 200 mm amplitude.
yeah, I think so. You are, yeah,
Because this is a assignment question, ma'am. If you
yeah.
uh,
Like, but this is this week's assignment, so like
uh,
technically I cannot discuss it, but I think so. You're in the right track.
okay, okay,
So,
thank
any other specific doubts from week two content? Any pain points there? And were the questions which ma'am discussed, were those questions clear? So any comments on that? Otherwise, we'll also pick up some questions and we'll try to solve them so that basically you have a bigger. Uh, the more you solve the questions, the more idea you have. So, were the questions
Ma'am,
clear? Any comments on that?
I have not done week 2.
You should have watched week two's lecture.
I have watched.
So please like try to make it a habit that you see the lecture once and you come, so that when we discuss it, understanding it becomes easier. Because otherwise you'll be lagging behind. So
Yes, ma'am.
it's fine. Like just at least use the Tuesdays discussion hour. Try to finish it before Tuesday so that you can uh, discuss it with one more TA who's there. So okay, let's pick up some question and we'll do. Mm, For any specific, uh, we have one more participant, and I think so. He has studied week two's lecture. Any specific area which you want me to touch upon, or
Yeah,
any specific problem like Coulomb's friction? Like, should we discuss theory or should we do questions? Because, like, what are your comments on that?
yes, ma'am. Solving problems would be beneficial for us.
Okay, then let's pick up some question and let's do it.
Sir, you have done all the videos of week 2.
No, no, no. Partially done up to harmonic vibration. Lecture one I have done. So,
Will it be okay if ma'am just provides an overview and then we go into question?
yes, yes. I'm
Overview, overview is just maths. Even if we do the question, you'll get the idea.
Okay.
This, yeah, you'll have an idea, but please try to go through the lecture
Yes, yes,
before the
sir.
next thing. So, okay, I'm trying to find something somewhere we can start.
mainly, ma'am, it is part of solving differential equations of
Yeah,
various parameters.
it's dynamics. Like this portion of dynamics is just solving differential equation. Here the differential, it's single degree of freedom so you have only one variable. It would have been a multi-degree of freedom. Some more difficulties come into picture. Otherwise, it's uh,
Yes.
okay. Uh-huh. Power. So let's discuss the half power bandwidth method and let's do one question from there. So, like, so half power bandwidth method, it's a technique. It's one more technique to find out the damping ratio. Like here, this is the logarithmic decrement method, which is used to find out the damping ratio, and this is one more technique which is based on the forced vibration thing. And what is forced vibration? In free vibration, motion was happening because of the initial conditions imparted on the body. Here force vibration happens because of you have a force acting on the body. That is why, simply put, that is why that is the source of the motion. So if we start with forced vibration. In forced vibration, also you have damped forced vibration and undamped forced vibration. So, if you think about undamped forced vibration, I'll write down a few equations and then we'll get into the problem. Otherwise, like directly picking up from there will be uh, difficult. So, for undamped forced vibration, the system is you have a same thing And now you have a force acting on this body. So the differential equation which you are solving is mx double dot, sorry, mu double dot plus ku is p of t. And suppose p of t is of the form p naught sine of omega t. So the solution of this differential equation will compose of two parts. You'll have a complementary solution and you will have a particular solution. Complementary solution meaning when the right hand side is 0, and particular meaning when you have this forcing function sitting on the right hand side. And u will be uc complementary plus particular. U complementary comes from here, which is nothing but the solution of the free vibration problem which we have already done. And u particular is when you are solving this differential equation. um, and this you can solve, like this was done in the lecture. That part I'll skip. For that, that here the thing is, for you particular, you assume a particular solution, and like what we did in the for free vibration case, you assume e to the power st. Here also you are assuming some form, that u particular is, let's say, c sine of omega and t. Take the derivative, substitute it, get the solution, and your solution will be of the format u is equal to, your u complementary is a cos of omega n t plus b sine of omega n t, plus particular solution is p naught by k 1 by 1 minus omega by omega n whole square sine of omega n sine of omega t. So this solution is applicable when omega is not equal to omega n. Otherwise, this denominator will go to 0 and the solution will not make sense. So, when you find out that particular solution, this is a restriction there. What happens if omega is equal to omega n? A term known as resonance happens, solution blows up. We'll see that as well. And here again, how do you calculate A and B? Use the initial condition and you can figure out A and B. So finally, you will get the solution of the form u0 cos of omega nt plus u naught 0 by omega n minus p naught by k omega by omega n 1 minus omega by omega n square. Like this is the entire b term, sine of omega nt plus p naught by k 1 by 1 minus omega by omega n whole square sine of omega t. So as you see, this part of the equation, this part is known as the transient part and this part is known as the steady part. Why these names? Steady part because this, let's call this second term, and for 2 and 1. This 2, here you have the forcing frequency omega coming into picture. And in the first part, you don't have the forcing frequency. Because of constant, it appears, that is fine. It comes into picture. And with time, this first part will die out. And that is why it is called transient. And this will always remain in your solution. So if to give an idea of what this means, your second part, uh, your transient part looks, the second term, which is the steady state solution, will look something like this, which has a frequency of omega, and this transient has a frequency of omega n, and it will be something uh, which is superimposed on this, and your total solution will look something like this. So because of this, this will be your total response. And with time, okay, so this is an undamped situation. So here it will not die out. But when you look at the damped solution, damped forced vibration, this first term will die out. That is why the term transient. Now let's say your initial conditions are 0. That is u0 is 0 and u0 0 is 0. Then also you will have a steady state solution, and I'll write this, and you will have this term as well, that is the transient. So these two portions will still be there even if the initial conditions are uh, 0. So okay, so now maybe we can pick up one problem. So in the half power bandwidth method is okay, I'll have to introduce one more term, that is RD. So here u of t, which we were studying, can be written as, let's say the initial conditions are 0. So you can write this as p naught by k, okay, this term, 1 by 1 minus omega by omega n whole square. Then you will have this sine omega and sine omega t minus, you will have omega by omega n sine of omega n t, right? And let's say this is the total solution, this is the steady part, and this is the transient part. Let's say that um, uh, uh, this being undamped, this is not dying out. If this would have been damped, this term would die out. So now let's consider only the steady state part of the solution. That is u of t is p naught by k by 1 minus omega by omega n whole square sine of omega t. Now, I want to introduce a term, uh, u static, which is happening because u static is because of this force, let's say with the amplitude p naught. Uh, because of a force having an amplitude p naught, what will be the deformation? That is u static. So u static is p naught by k. So what I can write is u static, let's say as a function of time, will be this p naught by k can be written as ust into this term. I write it as rd, which is kind of a factor which is telling me whether my static response, because of this static means force is not changing with time. The force applied is p naught. Now the force is p naught sine omega t, which is a function of time. So because of this force, whether my response is increasing, decreasing, that is whether it is getting amplified or de-amplified. So I can write it in this format. So this is the term which I wanted to introduce, that is RD, and the terminology used is the deformation response factor. RD is the response reduction factor. Now let's use this response reduction factor and understand what is this half power bandwidth method. In the half power bandwidth method, which is a technique to calculate damping, you plot RD on this axis, that is this expression, and you are varying omega by omega n. So, and what is observed that when omega and omega by omega n is 1, it like when omega by omega n is 0, here the value is 1. So the plot comes out to be like this. This can be experimentally measured. Like this is a technique where you can plot this graph experimentally. You can do some experiments in the lab and you can plot this. And from that plot, you can calculate the damping. So uh, at this point, you know that this is the resonant amplitude. So what do we find? Let this resonant amplitude be some A. So here a point, like we draw a line where the resonant amplitude is 1 by root 2 times A, and these 2 points are noted. Why is this done? Because this is how basically we are relating the power in the systems, and these 2 points are marked, and they are this is known as, this distance is known as half power bandwidth, and it is equal to 2 zeta. So 2 zeta is equal to, let's say this is omega A by omega n, and this is omega B by omega n. So this is omega B by omega A by omega n, and from here you can calculate zeta. Zeta is omega B minus omega A by 2 omega n. So this is a basic idea of the half power bandwidth method. And the there here I talked about the response reduction factor RD. There are other factors as well, like RV, RA, and this has been discussed in the lectures. For this context, I just need RD. That is why I discussed that. So let's do a question on this. Just hang on for a second. I'll pull out the question.
Ma'am, this RD is taken 5 in IS 1893. Can you tell me what is the logic behind it?
That is, and that and this is different.
Okay, okay, okay.
Mm, not completely different, again, not
But
completely
it,
same.
yes,
The
yes.
terminology is same. There also we call it a response reduction factor, but
Hmm.
that is, see, the basic, I'll just uh, summarize it very shortly. Suppose we, under earthquake, we don't want to make elastic structures. If we make structures to be elastic, it will be extremely, the sizes will be extremely heavy, and we are telling that it will be uneconomical, because uh, like first is uh, the probability of occurrence, like under earthquake we are ready to accept some damage. So what we do, suppose under a given, let's say, earthquake excitation, we know that this is the force F and this is the delta, this is the deformation, let's say this being delta, this is expected. Instead of designing for this force, you reduce this force by a certain quantity, and the factor by which you reduce is this response reduction factor. And this F is the base shear which I'm talking about. Instead of designing for a base shear F, where F is the base shear required if the forces, if the structure has to remain linear elastic. Now I don't want my structure to be linear elastic. I accept the fact that there will be a certain damage, and my structure can take that damage, and because
Oh,
of that we do, let's say in concrete we do ductile detailing, and let's
yes.
say we reduce the force by a certain factor R. We reduce it by that factor, and in because of that, let's say my uh, deformation in the structure increases, let's say it can take it. So this is that response reduction
Okay,
factor
okay,
which is there in the book.
okay, okay.
So suppose you have a frame, and okay, so you are given the data that, okay, maybe we can't use this data because uh, a lot of plotting will be involved in this. I'll just explain the context of the question so that so one experiment, let's say some experiment is being done, and let's say you have a frame like this, and you mount it on a table, shake table in the lab. You apply the shake table, and you are applying certain ground acceleration, and that is varying with time. And what you record is, suppose you record the acceleration versus time, and you see something like this, that your response is something like this. When you do something in lab, there will be damping and things will damp out. So let's say here you see that ui double dot is 0.915 g, and let's say this is at certain time, and these peaks are basically known. Basically you have these data points, right? And then using this data, you can plot the this kind of plot, this response reduction, this rd versus omega by omega n plot. Now for ground acceleration, you have a term called transmissibility. We'll just discuss that. Let us discuss that, and then we'll get back to the question. So what is transmissibility? Here we are studying the thing. Suppose, like, okay, first I'll ask this question. So have you gone through the concept of, like, till date, whatever, what did we do? We had a body and we applied force on it. Instead of applying force on a body, what if I apply a ground uh, acceleration or ground displacement? First, is the analogy between the two systems clear? If not, first we'll discuss that.
Yes, ma'am. First, we discuss that analogy because we
Okay,
haven't gone into that.
okay. So uh, so let's consider a frame like this. If you have a frame like this and you have a force P of T acting on it, so till date, whatever we have studied, and there is a damper as well, a viscous dashpot, and effective stiffness is K. So we write mu double dot plus cu dot plus ku is equal to P of T. Till date, we have studied this. Now, instead of this, suppose you have a system like this, and your ground is moving. You apply UG. When your ground is moving, your frame will also move, and it will have certain effects. So let's say your ground is moving till here, your frame displaces like this. So from initial point to the final point is the total displacement, which is this much is u ground and this much is u, or you can say the relative uh, ug is the ground displacement and u is the relative displacement. So u total is equal to u ground plus u. Is this fine? This you can write that total displacement is displacement of the ground plus the relative displacement. Okay. Now I want to write down the same thing which we did earlier also. I want to make a cut here and draw the free body diagram for that mass. So for this mass, so you will have some spring force, then you're cutting the damper as well, you will have the damping force, and you will have certain inertial force. No external forces acting on the system. So Fi plus Fs plus Fd is equal to 0. Fine. Now inertial force is mass into acceleration, and acceleration is total acceleration. M into ut double dot. Right. Now, and what is spring force? Spring force is K into U. It is the relative, like suppose you have a spring, initial length is X, then you pull the spring and make the length to be X2, and the length becomes X2. Initially, the length is X1. So, what is the force required in increasing the length from x1 to x2? It is f of x2 minus x1, or you can say the relative displacement only comes into picture. Here also, how much is the displacement, relative displacement between the mass and the ground? U. So, Fs will be k into U. Similarly, damping force is also is c times u dot, or the velocity, which is also here also only the relative term should come into picture. So Fd is C into U dot. So let's substitute these terms. So Fi is Mu double dot total plus Cu dot plus Ku is equal to 0. Now let's substitute this here, that Mu double dot T is Ug double dot plus U double dot plus Cu dot plus Ku is equal to 0. So Mu double dot plus Cu dot plus Ku is equal to minus Ug double dot. So if you compare this equation with this equation, the similarity is in when the ground is moving, your effective force, or P of T, is minus Mug double dot. So this is the similarity between these two systems, that when the force is acting, this is your differential equation, and when the ground is moving, which happens in earthquake, this is the force which is acting on the system. So is this clear?
Yes, ma'am.
Okay. So then we'll briefly touch upon transmissibility. Transmissibility is just how much force is being transferred to the support. This is simply what transmissibility means, and then we'll look at the question so that you understand half power bandwidth, how it is done in the lab. So, mm, so let's do check the notation followed in the class so that I don't complicate things. Yeah. So for force transmissibility, the thing is, suppose you have suppose you have a mass sitting like this. There is a spring and there is a dashpot. And this is your variable x, mass m, and you are applying a force P naught sine of omega t. Because of this P naught sine of omega t, you have to calculate how much force is transferred to the base. This is simply force transmissibility, and this is studied when you have to, suppose you want to do vibration isolation. Suppose a machine is sitting on the floor in a factory, let's say it's sitting on a floor, and because of the machine, suppose it has some rotors or something in it, because of which there is a periodic force generated in the machine, and because of that, foundation, let's say, is subjected to a periodic force, but you don't want that force to basically you want to isolate the vibration, or you want to or let's say you want to dampen that vibration, so you can use base isolators or those things, and the basis of all those comes from here. So let's first understand what force is getting transmitted, and then we look at the expression. So what is the force transmitted to the base, ft? So if we make a cut here, what ft will be equal to force in the spring plus force in the damper. So it will be force in the spring plus force in the damper. So what is the force in the spring? Force in the spring will be k into x, and in the damper it is c into x dot. Now, what is under this situation? What is x when like a mass is subjected to a force p? We were deriving the expression, which is p naught by it is this expression. This is when a mass m is subjected to a force p of t. What is the expression? Assuming that the initial conditions are zero. So we can write this. So under this thing, we said that u of t is equal to p naught by k, 1 by 1 minus omega by omega n whole square, sine of omega t minus omega by omega n, sine of omega n t. This is the entire solution. And how can we uh, write this? This can be written as P naught by K. This term is written as RD. And let's assume that we are dropping this term, this steady state, the transient term. We just keep the steady state term. And let's, for the sake of generality, let's have the phase angle also into picture. For this case, the phase angle will be 0. If there is damping and if you manipulate the equation, here you have damping, because like when we were writing this expression, it was without damping. But when, sorry, here when we are studying transmissibility, you have a damper. So if you go through that expression, you'll understand that x is p naught by k r d sine of omega t minus phi. Let's just at this stage, let's accept that this is the solution. Then we can substitute those this x back into the expression above, which is p naught by k r d. Then this k times sine of omega t minus phi plus cos of, take its derivative. You have cos of omega t minus phi, and you have a c omega term as well, plus c omega. Okay. So from here, again, we'll use the same concept which we discussed. We'll take this term and this term, and we can calculate and we can combine it, and we can write it in the form of x sine of some omega t minus some new phase angle phi dash. And uh, here you will also have p naught k r d. So what will be the amplitude of the force F? Amplitude amplitude of the force transmitted will be p naught by k r d, and you will have this x. What is this x term? X is k square plus c omega whole square. Because we have these two terms using trigonometry, I'm solving it. Now, let's say this force transmitted is some Ft naught. I can write Ft naught by P naught to be Rd times here throughout, let's say divide by, mm, let's bring this k inside. So you will have 1 plus c omega by k whole square, and this can be written to 2 zeta omega by omega n whole square. So this is the expression for Rd, and this is the expression for amplitude of the force transmitted. So what is, so I'll just check if I have a question on this. Or in other words, transmissibility, I'll just write the expression. Transmissibility is equal to, just hang on for a second. Missing something. Okay, yeah. And the transmissibility of the system is defined as 2 zeta omega by omega n whole square by, so like from previous knowledge, since I've not discussed uh damped, I did erase this. Rd is 1 plus 2 zeta omega by omega n whole square. Now, from previous knowledge, like when you will study, I'll write down that topic, damp force vibration. See, we studied undamped force vibration, undamped force vibration, and for that we calculated the expression for RD, and we found out that the expression for RD is 1 by 1 minus omega by omega n whole square. RD, did I show the expression? I think so, I did not show. Yeah, we had derived that RD, the response reduction factor, is 1 by 1 minus omega by omega n whole square. 1 by 1 minus omega by omega n whole square. When you do the forced vibration analysis, you will see that the expression for RD is 1 by under root of 1 by omega n whole square of that, plus 2 zeta omega by omega n whole square. So here in this ratio, I want to substitute the expression for RD from here, and this ratio is known as transmissibility or TR. And if you use that, so you will have, let's substitute RD, which is this 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square, and from here this numerator will come here under root of 1 plus 2 zeta omega by omega n whole square. So let's quickly do a question that suppose you have a very sensitive instrument and its weight is 100 pounds, and it is to be installed at a location where the vertical acceleration is zero point 0.1 g at a frequency of 10 hertz. So I'll just write down the salient points in the question. So you have a instrument with weight 100 pounds, and it is to be installed at a location where vertical acceleration is 0.1 g. Vertical acceleration is zero point 0.1 g at a frequency of 10 hertz. At a frequency of 10 hertz. This instrument is mounted on a rubber pad. Okay. Instrument mounted on rubber pad. Just check. Yeah. It's mounted on a rubber pad, and the stiffness of the rubber pad is 80 pounds per inch, and the rubber pad has a stiffness of 80 pound per inch and damping such that the damping ratio for the system is 10%, and damping so that damping ratio of the system is 10%. Damping ratio of system is 10%. You have to find out what acceleration is transmitted to the system. First question is what acceleration is transmitted to the system. Second question is if the instrument can tolerate only an acceleration of 0.005 g, you have to suggest a solution assuming that same pad has to be used. See, if instrument can tolerate only uh, an acceleration of 0.005 g, you have to suggest a solution using the same rubber pad. Suggest a solution. So first is how much acceleration is transferred to the system. So here I'll quickly tell. So here whatever we derived was in terms of force, how much force is transmitted. The same is applicable for acceleration as well. You can so ground acceleration is same as the transmissibility expression which we derived here. This transmissibility expression for force is same as that for acceleration. Here we did it for force. That uh, and for this question, since here you have to calculate how much acceleration is transmitted, we are using it's the same expression. Uh, this you can derive. Otherwise, I'll quickly do it after solving this question. So first, what is given? That the stiffness is 80 and the mass of the system is given. So you can calculate the natural period of the system. So let's start with the solution. So omega n is under root of k by m. Stiffness is 80 pounds per inch. Mass is 100. It's in weight, so convert divided by 386, that is g in inches per second square, and this you will get to be 17.58 radian per second. Now you know omega n, and you have what is omega. Omega, it is given that it is at a frequency of 10 hertz. So if you convert it, it will be omega is 2 pi by time period, and 1 by time period is frequency, and frequency is 10 hertz. So 2 pi into 10, so 20 pi. So omega by omega n, you can simply calculate 20 pi by 17.58. This comes out to be 3.575. Now, using this expression, why we are using the expression, I'll just uh, derive. Using the same expression, you can calculate the transmissibility ratio, which is the ratio of the like for here the transmissibility is how much force is transmitted to that of the amplitude of the force that is being applied, how much force was being applied, p naught sine of omega t. So you're dividing by p naught, that is the amplitude of the force. So here similarly it will be total acceleration that is being transmitted to that of the acceleration of the ground, and use the same expression. So it will be under root of 1 plus 2. What is the damping? Damping is 10%. Damping is 10%. So let's use it. So zeta is equal to zero point 0.1. So this is 0.1, and omega by omega n is 3.575. Square of this expression divided by, to be just clear, I'm using this expression. 1 minus omega by omega n is 3.575. Square of that, again whole square of that, 2 zeta is zero point 0.1. Omega by omega n is 3.575. Square of that. So your transmissibility comes out to be 1 point this much. And in the question you have been given that the ground acceleration is 0.1 g. So just use that. So you can get,
Excuse me, ma'am. Can
yes.
you please draw the problem? Can you draw the figure so that we can comprehend the actual problem? Actually, we are not
Okay.
able. I'm not able to figure out the what are the demand of question.
So the system is, suppose you have a mass like this. It is sitting on the ground, and this ground is accelerating, the vertical acceleration. So this is clear, that the weight of the instrument is some 100 pounds, and it is subjected to a vertical acceleration of zero point 0.1 g at a frequency of 10 hertz. So uh, here earlier, what did we do? We were applying a force of P naught sine of omega t. Instead of that, what is happening? My ground itself is moving, right?
Okay. Okay. Yes.
So because of that, because of this ground acceleration, I want to know how much acceleration is transmitted to the system. Or you can say at this level, like at this level, like my body is subjected to what acceleration.
Yes. Yes. Now got
So
it, ma'am. Yes.
this is what I'm trying to calculate. So like just plug in ground acceleration, that is 10 hertz. Sorry, ground acceleration is zero point 0.1 g. So zero point 0.1 g into transmissibility ratio is this number. So in this way, you get that when, so what is, like what do we know from this question, that when there is a vertical acceleration of zero point 0.1 g at a frequency of 10 hertz, the acceleration transmitted to the body is 0.01 g. So with this transmissibility, I could calculate that. But let's say my instrument can handle only this much acceleration. It cannot take 0.01 g. So what will I do? I have to somehow change my this transmissibility, this ratio. In this ratio, what can I change? See, either I can change my mm, either I can change the stiffness, the damping, or I can change this omega by omega n. What are the factors in this equation? In this equation, the factors of appearing is omega. You can change for a system. You cannot change omega. Omega is the exciting frequency, so that is fixed. What you can change is omega n and zeta. But let's say you are using the same rubber pad. So the damping ratio also can't be changed. So the only thing you can change is the natural frequency of the system. Now what is, so the part A is done. In part B, you are trying to change omega n. What is omega n? Under root of k by m. So let's say I am adding certain, since I'm using the same rubber pad, its stiffness can't be changed. I'm adding some more mass into the system. So let's say you are adding, earlier the mass was 100 pounds, you add some another 150 pounds in the system. Then this omega n will change. When this omega n will change, uh, this transmissibility ratio will change. And finally, I want to bring down my acceleration transmitted to this number. So suppose I add a mass MB of, let's say, 150 pounds per g. So the total mass will be, earlier I had 100, so plus 150. So, okay, I hope this is visible. Therefore, new omega n dash will be, stiffness of the system is 80. Earlier mass was 100 by, yeah, earlier was 100 pounds plus 150 pounds divided by 386. This comes out to be some 11.11 radian per second. and then you can calculate omega n dash by omega. Sorry, what are we using? Omega by omega n dash. Omega by omega n dash. See, in the formula you have omega by omega n dash. Omega remains the same because it is the exciting frequency. What is the exciting frequency in the problem? It is 10 hertz. What 10 hertz is being converted into radians per second. This is in radians per second. You get 20 pi. So 20 pi divided by the new frequency. New frequency is 11.1111, which comes out to be 5.655. Now using this new uh, omega by omega n dash, you can calculate again this transmissibility. And when you do that, uh, you will find that this ratio has gone down also. Okay. Apart from this, you will also need the new damping ratio. For that, let's say uh, earlier the damping ratio zeta was zero point 0.1. Okay. Now we know that zeta is equal to C by 2m omega n. From there, you can calculate the C of the system. What is C? From here, zeta 2m omega n. Why am I doing this? Because in the transmissibility ratio, while for calculating this, omega n has been changed, done. Now the zeta has to be figured out. Zeta will change because I am changing the the few. I had just told that we cannot control zeta. I would like to uh, correct that. We can change zeta as well. I am very sorry for that confusion. So here what we are doing, in order to bring down the acceleration, we are changing the transmissibility ratio. First we want to change that. To change that, I will first change this omega n, the natural frequency of the system. And to change, when we change that, my zeta has to be changed. And what is zeta? We just wrote zeta is C by 2m omega n. Mass of the system is changing. So for that, I first need to know how much C was actually present in the system. So if you plug in the values here, zeta is zero point 0.1. Mass of the system earlier was 100 pounds by 386. And omega n earlier was 17.58. Why I'm doing this? Because I want to know how much C was there in the system before. So from there I calculate 0.911. Numbers are fine, just get the concept. Now I put the C here, 0.911, and this will be the new mass of the system, which is 250 by 386, and this omega n will be the new damping of the new natural frequency of the system, 11.1111. From here we get the damping of the system changed to 0.063. So using this damping ratio and using this frequency ratio, when you calculate the transmissibility ratio, it is found that it is equal to 0.04. So the total this you know that transmissibility ratio is the ratio of this term. Now ground acceleration in the question, it is given that this is 0.1 g. So what is the total acceleration? What is this numerator? This means the total acceleration that is transmitted. So this is equal to 0.004 g, and your limit was 0.005 g. So we have been successful in reducing the acceleration transmitted to the system. So okay, there is some issue. So we have been successful in reducing the acceleration transmitted to the system. I'll quickly take